All right, welcome back. We are implementing a linked list so that we can compare its performance to an array list. Previously, we implemented the node, that is the central element of our linked list. Nodes will get chained together in this way to create a linked list. What we need to do now is we need to wrap this in a linked list architecture. What this is going to end up looking like is we're going to move these nodes into an inner private class so that our linked list class will actually hide these within it, like so, the outer class being called a linked list. Internally, the linked list will keep track of nodes, but the users of the linked list don't know that there are nodes internally as part of the implementation. So what we'll do is we'll go over to Eclipse and take a look at what we have there. Now the first thing that we want to do is we want to implement the interfaces that describe what an abstract list is going to be. And this is going to be, regardless of whether it's an array list or a linked list, we're going to specify the things that it contains. So this is going to be an interface called list. Finish it up, open it out. And the things that we're going to add are those methods that we described when we were walking through the first video in this segment. Go ahead and add these in here and walk through them one at a time. All right, so for starters, this is an interface. And so what that means is we're describing the methods that must be present in any class that implements a list, however it chooses to do it. So we said that the first thing that a list must do is it must be able to get the first and last elements of its list. So in the interface, we describe what getFirst is going to return, something of type object, and we describe the parameters that it's going to take, which are none. There are no parameters. We put a semicolon at the end because we're not implementing it. We're not putting any code there. We'll go ahead and put some Java doc here as well, describing what this is supposed to do. Notice that if there is nothing in the list, this is a list with no elements, this is going to throw a no such element exception. So getFirst and getLast give us the first and last elements of our list. Similarly, removeFirst and removeLast will remove the first and last elements of our list. When we want to add something new to our list, we can put it at the beginning by using the addFirst call, or we can put it at the end with the addLast call. Finally, if we would like to figure out how large our list is, we can call the size method, and that will tell us how many elements are in our list. And if we want to get a particular element in our list, we can call get, and that will get us a particular element that's present. We would also like to be able to get more nuanced control over walking down this list and doing different things along the way. And to do that, we'll call getIterator, and that will return us an abstract list iterator. Now Eclipse is highlighting that in red because we don't actually have a list iterator interface defined. So let's go ahead and define a list iterator interface. Just like the abstract list, we don't know exactly how this is going to be implemented, but we know the different things that it has to, the behavior that it has to have in order for us to be able to work with it, regardless of what the underlying structure is of the iterator. So here's our iterator, and let me move some of this code over from my pre-cooked version. We'll drop this in here, and we'll see that we have the various methods that we talked about previously. HasNext returns true or false if the current position of the iterator in the list will return a valid element the next time that we call next. So HasNext is either true or false, and if it's true, then when we call next, we'll step over an element and return that element that we walked over. Likewise, if we have an iterator and we would like to add an element to it, we'll add an element before our current iterator position and move it past it. Finally, if we want to remove an element, we first must have called next to walk over an element, and when we want to remove it, we can call remove. Depending where our iterator is positioned on our list, we'll remove different elements. Finally, if we've walked over an element previously by calling next, we can call set, and that will change the data that's internal to that element along the way. So this is abstract. Again, we have the return types, we have the signatures that they have, possibly some parameters, and there's no implementation, so it ends with our semicolon. What we want to do now is we want to talk about implementing a specific kind of list. We want to implement a linked list. Let's go ahead and do that. Go ahead and select our package, and we'll say we would like a new class. Our class is going to be called linked list, and it will use the interface of a list, the one that I just created. And great, finish that up. And what you see we get immediately is we get all of the methods that were described in the interface stubbed out, but they don't have an implementation because we don't know how to implement them yet. And they also have a bunch of to-dos reminding us that we need to fix them. Okay, fair enough. So let's go ahead and think about what it is that we want to include in our linked list. This is going to be a doubly linked list. And so what we're going to keep track of in our linked list is we're going to keep track of the first and last elements that are present, the beginning and ending of our list, of our linked list, right? Okay, so what that means is that internally in our linked list, we're going to keep track of a data point called first. Go ahead and spell it right. And first will point to the first element in our chain. And we'll also have a variable called last that will point to the last element in our chain. And if all goes well, we can keep those up to date as we build our list so that we can rapidly get to the beginning and the ending of our linked list. Okay, so in our linked list then, we're going to want to add, let's go ahead and put some Java doc at the top of this here, describe what we're doing. And let's go ahead and add those first and last elements. Those are going to be our variables that point to the beginning and the end of our list. We want our node to be a private class that only this class can use. So now what I'm going to do is I'm going to move the implementation of the node that we previously created in a separate file, and I'm going to drop it in here as a private class. So I'm going to go over to this file. I'm going to select everything from public class node down to the bottom. I'm going to go back to our linked list, and I'm going to paste it here on line 16. Then I'm going to remove the word public, since this is going to be an internal class. I'm going to go ahead and format it so it gets properly indented. And then, just so it's not confusing, I'm going to click the little minus sign here to collapse the definition of node into one line. That eliminates a lot of clutter in our code and enables us to see clearly what's happening. Then I'm going to go ahead and delete the external definition of node and node test. That was helpful while we were building it out and debugging it, but now that we've moved it inside of our class, it's a little bit trickier to test it. So go ahead and I'll delete those. All right, and then clean up our imports. And clean up our imports. All right, so the first thing that we need to think about then is we need to think about how it is that we want to initialize our linked list. And initializing our linked list typically would take place in a constructor. So let's see if we can build out a constructor for our linked list. A linked list reasonably in our constructor should initialize a bunch of elements. And in this case, initializing a bunch of elements just means, because we have nothing in our list when we start, it just means initializing first and last to null. So we'll go ahead and create a constructor that makes an empty linked list and sets first and last equal to null. Get first then becomes a fairly easy method to implement. All we have to do is check to see whether first is equal to null, and if it is, throw an exception, and if it isn't, return the node that we point to. Now again, because we don't want our users of linked list to realize that we're operating with a node, we don't return a node here, we return the data that is stored in the node. So if first is equal to null, then we throw an exception. But if it's not, then we get the first node, and we call the getData method on the node to just return the data so that the person using the linked list doesn't realize the complexity of how we're implementing it. Similarly, we can do the same kind of work with getLast. In getLast, we will check to see if last is equal to null. And if it is, then we'll throw a no such element exception. And if it isn't, then we'll go into our last element and we'll get the data associated with it. Okay. Now removing our first and removing our last element are a little bit more complicated. And so maybe the first thing that we'll go ahead and imagine that we're going to add our first element instead. We're not going to imagine anything, we're just going to do it. We're going to implement add first because it makes a little bit more sense. All right, when we add our first element, what we're going to do is we're first going to create a new node, and that new node is what we're going to put at the beginning of our list. So if we cut over to our diagram, here's roughly what we intend to do. Let me see if I can do this cleanly. Okay. What we hope to do here is with some kind of existing list that's present, we're going to add a new node. And so this will all happen inside linked list, but for the sake of clarity, I'll go ahead and draw it outside. We'll create a new node. We will set the data equal to whatever the data was passed in. And as long as this first element here points to something, we'll go ahead and say that new node.next is going to point to whatever first points to. Same thing. And we'll say that first's previous is now going to point to here. And we'll say that the new node's previous is going to point to null, but of course that's how it gets initialized. And then finally, we'll move first so that first points here, giving us the final construction. Like this, we've spliced in a new node, keeping all of the semantics of our different links accurate so that future calls to any of our functions are going to work okay. So what does that look like? All right, well, there's the special case where there's nothing present in our list, in which case first should point to the node we made and last should point to the node we made, creating a list of one element out of nothing. But if we already have something present, we'll go ahead and set the next element of our new node equal to whatever our linked list was previously pointing to. We'll set the previous element of what was the first node equal to our new node, and then we'll set first equal to our new node, completing the splice process. Well, add last is very similar. It's just we switch out the previous and the next because we're dealing with the end of the array, or the end of the list. It's not an array. So here's an example of how we're going to do that. In add last, we also create a new element. And we're going to, this is very similar to what we just did a second ago. We're going to create an element over here. Oops, let's see if I can get this to draw. Go ahead and use something that you draw with, for example, a pen. We're going to create a element off the end. We'll store the data, we'll look at next, and we'll look at previous. And we'll say that whatever our previous is going to point to is going to point to whatever last points to. We're going to set whatever our next element and last, we're going to have that point to the element here. And then we're going to change last so that it points here, and next already points to null, giving us a spliced in node at the end, like this, and like this. Creating a node, creating a list, that's one longer. All right, so how do we actually do that? Well, we create our new node here. Here's where we add the data to it, and we initialize next and previous to null. And then we immediately go about trying to change that. If last is null, then we have nothing in our list, and we go ahead and set the first and last element of our linked list to this new node. If we do have elements in our list, then this new node that we're currently created, its previous will be what was the last element of the linked list. The next element of what was the last element is now going to be our new node, and finally we'll set last to point to the thing that we just created, thus creating our add first and our add last. Okay, well, there's a very similar process for removing our first and removing our last element. Let's move that in here. When we want to remove an element, what we're going to do is we're going to want to return that element. So the first thing that we're going to want to do is we're just going to want to create a little local variable that's going to point to the element that we're going to remove from our first element in our chain. That's just to make sure that we don't lose track of it. Then what we're going to do is we're going to see if first and last are the same. If first and last are the same, then they're pointing to an array, a list that only has one element in it, in which case we're just going to remove that element. But if there are more than one element, then what we're going to do is as we remove the first element, we're going to say that whatever first points to here is now going to point whatever first, we're going to change first, so that instead of pointing to this element, it points to whatever this element's next points to. So we're going to follow this chain here and just bypass it, so that first points to this element. And then we're going to change the first element. Now we're following this new chain and set its previous and set that equal to null. That's going to cause us to splice out this element here, splice out this link here, and then we're going to go ahead and return this element as the result, and as soon as we lose reference to it, the garbage collection will clean it up. But we might not lose reference to it right away because we're passing it back as the return of this function. Okay, so let's look at what that looks like in code. We first to check, make sure that there's something in our list. If there's nothing in our list, then we have an empty list and we're trying to remove something from it. So according to the specification, we throw a no such element exception. The second case is if first and last are equivalent, meaning that we have a list of length 1. If that's the case, then we just set first and last equal to null after getting a pointer to the data that's associated with our node. If first and last are not equal, meaning we have a list with more than one element in it, then we go ahead and do that splicing that I just showed you. We make first equal to what first was previously pointing to, and then that one's next element. So we splice out the first element, and then we set the previous element of what we just made the first equal to null, splicing out the previous data. And then finally, once we've done that link rearrangement, we return the element that we have just pulled off. Well, remove last ends up being very similar. It's got a parallel pattern to what we just saw. If there's no element, we throw a no such element exception. We grab the data that we're interested in removing. If there's one element, we create an empty linked list as a result. But if there's more than one element, then we follow those pointers to first of all update what last points to, and then update what the new last element points to, so that we drop the element that was previously last, setting the next element, the second to last element, equal to null. That gives us the remove last element. Okay, so that's pretty good. What else do we have to implement here? Well, abstractly, we have to return an iterator, and we have to do the size, and we have to do the get. Now, each one of these things, we can't really do get a particular element until we have an iterator that can walk down the list. We haven't implemented an iterator yet, so we can't actually return an iterator, and we can't implement size yet either. Where is size? I don't see, I must have erased size somewhere along the lines. We need to implement a size method as well, but we can't do that until we can walk down the list. So what we'll do in the next video is we'll implement an iterator, and we will use that iterator in order to calculate size and get, in order to return a get element. Okay, that'll be in the next video.